o'clock somewhere. So it must be 5 o'clock. All right. You know what today? Oh, Steve, you know what today is? Today is 5 o'clock. It's Q&A Friday. Why don't I have a Q&A over there? Do that. I gotta put an image. I don't know if I have Q&A Fridays in here. Hold on. Q&A Friday. No, I have to create a new image. Q&A Friday. Q&A Friday. And I'm going to add browse Q&A Friday. I got to go to pictures. No, not pictures. I've got to go to documents, then pictures. And then I go to, and I find Q&A Friday. There it is. Here we go. Open. Okay, here we go. Q&A Friday is what we call in the house as we speak. There it is, Steve. Hopefully everything is going well for you, my friend. Let me get up the chat. And I have to hit close. There we go. Man, I don't know about you, Steve, but I am. I had an exhaustive day today. It was, man. It was just there was a lot of task group work going on. Plus, I have a day job. Don't tell my boss, but I have a day job, and I've got to get my day job stuff done, and that was a nightmare. All right, so today, what I want to talk about, Steve, I had 3 items. One was the electric vehicle chargers. So, and I'm bringing this up because of a requirement in the code. You got to get your code book out. I'm going to be using the 2023 edition of this book. I want to be using the 2023 edition because I don't want to use the 2026 edition because we're still working on that. So, I had some interesting discussions around, so here's my thing. So first, we're going to hit 2020, first we're going to hit electric vehicle charging, and specifically, there's a requirement back here for electric vehicle power transfer. This is Article 625. And I believe the section number, hold on. I should know this because this is my program. Eden, man, where's it at? Where's my questions? Global, life safety, projects. I think it's projects. Is it projects? I don't know. Not that. It's not that. Anyway, so I had some questions come in about the markings on an electric vehicle charger. And the questions that came in were around the adjustments. So energy management. So we're going to talk adjustments. We're going to talk energy management. And I have to find my my materials. 26 maybe it was a 2023 GFCI. We had some marketing collateral topics. Nope. All right. Man, oh day. Steve, it's been a long day. I don't know about you, but it has been a very long day. All right, so I want to talk about EVSE. I also want to talk about I was listening to a video the other day, and it was on selective coordination. And you know, I don't know how, I know, Steve, how you operate. You listen to some of these things in the background. Well, I was doing the same thing. It was an interesting video. I thought it was an interesting video, and I still think it was an interesting video because it caused me to decide to go and talk about what I'm going to talk about. And in the discussion, the gentleman who was presenting brought up zone selective interlocking. And honestly, when I'm presenting in selective coordination, if I'm sticking to the topic of selective coordination, there's no reason to talk about zone selective interlocking at all. So I was just surprised that the topic came up. And when it came up, and then I tuned in. So then I stopped my phone, I backed up a little bit, and I started to listen. And man, I tell you what, it was wrong. And I'm like, I know I've covered it, but I thought, you know what? I'm going to cover it one more time. So that I want to hit that topic as well. So I'm going to hit that. I want to hit also, so selective coordination is in there. What was the third topic? I should have a piece of paper. First one was EV chargers. Second one, selective coordination. And there was a third one, and I cannot for the life of me think about what it was. But that's okay. All right. Let's, man, oh day. I am going to, why can't I find my document? Electric vehicle. I've had some dialogues with a few people from UL on this topic as well. And I think we might be in, I think it might be a good discussion point. Steve, you're something else. Or the 2026 code book. And you know, nothing is more frustrating when you can't find what you're looking for. Give me a second. There we go. I had it filtered the wrong way. Jeez, oh man, I'm looking at documents that are older than what I expected. All right, so the point of discussion, Steve, is in 625.42. Now, so this was the question. Oh, let me find 625.42. Rating. Here's what it says. Now, remember, you can have an electric vehicle charging equipment that when you install it, you can have a set point that will tell you what the current draw is, right? So the question comes up is, if I'm looking at a piece of electric vehicle charging equipment and it has a label on it that says 80 amps. This can handle up to 80 amps on a circuit that's rated for 80 amps, protected by, and it's a continuous load, right? So we remember what continuous load, definition of a continuous load. I believe it's 3 hours or more. I'm going to go up to Article 100. Continuous load, CON, T control connector control. Oh man, continuous load. Maybe you got to go load continuous. Gosh, I like article. You know, I like article. I like what they did by putting the stuff all in one. All in Article 100, all the definitions, but oh my goodness, load. Legally. Jeez. Load management. Listed. Where's continuous load? Now I gotta look it up. See if Steve, if you were paying attention, you could dial in. So this is the nice thing about NFPA Link. You go to NFPA Link, you go up to the top, you click on NFPA 70, and you do search, and you type in continuous load. I looked under continuous. I looked in Article 100 under continuous. That's the first place I went. What did I miss? ABC, continue. There it is. Jeez, oh man. A load where the maximum current is expected to continue for 3 hours or more. Ooh. Do you know why a motor? Can a motor be classified? I know this is off topic, Steve, but you know, when my, you know how I am, squirrel. I'm going to claim squirrel right now. Continuous load. A load where the maximum current is expected to continue for 3 hours or more. Hey, Ryan. Cheers, brother. So we're talking EV chargers. And Ryan Jackson, I went on a tangent at 5:00 p.m. Eastern on a Friday. I went on a tangent. So I was looking at 625.42. And I mentioned that, you know, you can have adjustable settings, and I'm talking about an EVSE that I can adjust in the field, so to speak. But I mentioned that an EVSE is a continuous load. So I said, oh, wait, what is a continuous load? Let's go to Article 100. Couldn't find continuous load. Now I found continuous load. It's in the C's, by the way. Continuous does not begin with a K, just so you know. And it says a load where the maximum current is expected to continue for 3 hours or more. And then it dawned on me, because I remember having another discussion. This is another Q&A. The question came in and said, Tom, is a motor can a motor be a continuous load? And I said, well, of course. It can be a continuous load because motors run for more than 3 hours. And then I looked at the definition. Well, the gentleman and I looked at the definition. And it says a load where the maximum current, and his point was the maximum current on a motor is the inrush current, and it doesn't persist for 3 hours. I'm like, oh my God, you're right. A motor that has a motor, it's going to have an inrush current. It's going to go away very quickly. And is that the maximum current? So anyway, that's another question. I'd love to know your thoughts on that one, Ryan. Can a motor have or be considered a continuous load? Even if the motor runs all day, can it still be considered a continuous load when the inrush current's really the maximum current and it doesn't run continuously? Is that why in 430 we have 1.25 in there a few times? Right, Ryan. 430, and so this was a revelation for me. I don't know why it was a revelation. I guess I've never been asked the question. And I've never used the code in that way to go, oh, this is a continuous load, I'm gonna do my load. No. You don't consider it a continuous load when you're doing your overcurrent protection and your conductor sizing, because Article 430, it tells you exactly what to do. So motors You don't do the 1.25 in motors for continuous loads like you would, because we are addressing that in 430. And another question, oh my gosh. So, I mean, I should write down the journey we're going here because, all right, so 430, continuous load. The other discussion that's going on in the code panel right now, task group work, due to some public inputs. We don't use, when we do a load calculation, I'm not worried about 1.25 times continuous loads when I do a load calculation to determine what? The size of a service and whatnot. I do the 1.25. Yes, you're right, Ryan. This is very dicey. So when you look at how we use the 1.25, you got to ask the question, why am I applying 1.25? So here's the thought process. If I do this, I got my iPad ready. Now, I don't know if this is going to work. I'm going to try this. I got a new setup. See that? Oh, wait, boom. Okay, it is working. Yeah. So if I have a breaker and I'm feeding a load, right? Now, when I size the conductor, when I determine the ampacity of the conductor, if it's a continuous load, I take 1.25 times that, and then I select my conductor based upon 1.25 if it's a continuous load, and then I pick my breaker to protect the ampacity of the conductor. Now, what's that done? What did that do? Now that's if I'm say 75 degrees C, etc., right? I've accounted for the 80% that my equipment is 80% rated. 1 over 1.25, right, is your 80% number. So I will use the 1.25 to pick my conductor size, which then I'm picking my overcurrent protective device size, unless it's all 100% rated. If it's 100% rated, I don't have to do the 1.25, right? So when I do a load calculation, I don't need to think about the 1.25 because all I'm thinking about are all of my loads, my KVAs. I'm adding them all up. And then I'm going to determine the size of my feeders and my size of my service. And I will, in a residential dwelling unit, determine the number of conductors. But if I am doing a branch circuit and I need this, and I go to 210 for branch circuits, right? So, ow, I almost poked myself in the eye. If I go to 210 for branch circuits, the rating shall be rated in accordance with the maximum permitted ampere rating or setting of the overcurrent device. The rating, where conductors of higher, I'm in 210.18. There's conductors 210.19, conductors minimum ampacity. This is where you get into, you do it with the multiplying factors, without, all that jazz. So I'm going to select my branch circuit based on this, but in the load calculations, I'm not worried about 1.25. I'm not worried about whether it's continuous or non-continuous. I'm using diversity factors, right? In 220, I get into the diversity factors. But I'm not, tell me if you think I'm crazy. Am I losing it here? I'm not thinking about 1.25 with regard to a load calculation based on a continuous load. I'm more concerned about sizing my branch circuit for the load, which you could. And throughout the code, in some places in the code, we'll say continuous load, and that assumes the 1.25 because of how I do my 210 and 215. right? You know, my Article 210 requirements and my Article 215 requirements, but when I do a load calculation, okay, so Ryan, you're saying, but if the equipment is 100% rated, that only works if the article says to consider the load as continuous. Right. When the rule, like 422.11, that's appliances. 422.11, let's take a look at what you're saying in 422.11. 422 appliances. Act now. 422.11 overcurrent protection. Appliances shall be protected against overcurrent in accordance with A through G. Holy crap. Branch circuits shall be protected in accordance with 240.4 if protected device rating is marked, blah, blah, blah. Household, electric heating. Well, so G is your motor operated appliances, so that's going to point to refrigeration equipment. If protective device rating is marked on the appliance, the protective device rating shall not exceed the protective device rating marked on the appliance. That's a given, right? So you can't, doesn't matter if you're 100% or if you're at 80%, you can't exceed that number. I was closed book, please hold. I was going to say, what you talking about? What you talking about, Willis? So anyway, the VA doesn't change, shock hazard. The VA appliance. So in any case, so we went from EV chargers and adjustable settings that the electric vehicle is a continuous load to what is a continuous load, and then the debate that we've had on panel 2 in Article 220, 422.13, 422 in Article 220 about whether or not you consider the continuous load when you do a load calculation. And you don't. 422. 422. 422.13. Storage type 1. Oh, yes. The branch circuit overcurrent device and conductors for fixed storage type water heaters that have a capacity of 120 gallons or less shall have an ampere rating of not less than 125% of the ampere rating of the water heater. Now, why would they put that in there? I can't double dip on the 125%. Is it the... Oh, geez, oh man. Ryan. And it says C422.10 for branch circuit rating. And 422.10 says individual branch circuits for the appliances. The branch circuit rating for an appliance that is a continuous load other than motor operated appliances shall not be less than 125% of the marked rating. So, and then 422.13 for storage type water heaters, it says shall have an ampere rating of not less than 125% of the ampere rating of the water heater. Do you have to double dip? You shouldn't. That's confusing. I hope you got some public inputs on this one. But in any case, so I'm going to go back to my EV charger. Go back to the EV charger. I have a, let's say that you have an 80 amp charger. It's rated for 80 amps. But it can be adjusted to other values smaller. When would you do that? You would do that if you're, say, you bought a new EV charger and your existing EV charger was 32 amps and your circuit was 1.25 times that, right? So what's 1.25 times 32? I should know this. 1.25, 32, I'm not good. 40 amps. Jeez, oh man. I knew it wasn't even a number. 40 amps. And for water heaters, how do I size the feeder? How dumb, 100% feeder, 25 amps to a fuse disconnect rated at least 30 amps. I know, Ryan, you're right. It's amazing. I think it needs some attention. And there is. So I believe it was Robert Osborne had a task group. And I'm not sure if there was a global on this, but there was and I know John McCamish was looking at this too. The use of continuous load versus 125% throughout the code. So in any case, I think in some cases we're double dipping, which is just bizarre. But in any case, all right. So back to this EV charger. So I might buy, let's say I have an existing EV charger in my house. It's on a 40 amp circuit. Its load is 32 amps continuous. 1.25 gets you to 40. I need 40 amps worth of conductor, and then I put a 40 amp circuit breaker on the device, on the equipment, on the branch circuit, feeding the EV charger. So now I upgrade. Okay, I go and I buy Eaton's brand new Cat's Meow. It's beautiful. It looks so awesome in my garage. I'm just buying it because it looks cool. And I buy this device and it's 80 amps and it said, hey, you know what? You can dial this down. So 80 amps, and I dial it down to 32 because it's on a 40 amp circuit and the continuous amps has to be 32 or less. So I put this in place, I dial it down. I don't want to change the branch circuit. I don't want to change my overcurrent device. I don't want to pull a new circuit. I just want to change it out. I'm happy with my car charger at 32 amps. I'm a happy camper. So can I do that is the question. And my answer was yes, you can. So, and then he says, I need a code reference. So I go to 625. And I'll tell you, this is where it got really confusing for me. So I go to 625.42 rating. It says the EVSE shall have sufficient rating. I'm in the 2023 code book. The EVSE shall have sufficient rating to supply the load served. Electric vehicle charging loads shall be considered to be continuous loads for the purposes of this article. Ooh, for the purposes of this article, does that mean when I'm doing my 210 branch circuit ratings, I don't have to worry about it? I don't know. Anyway, why do they say for the purposes of this article? What does that, what value does that add for the purpose of this article? I mean, if I'm going to do a 210 overcurrent device size and I'm going to do a branch circuit, I'm going to follow the rules in 210. Why does it say it's continuous for the purposes of this article? That's number one. I don't know about that one. And I just read it, and anyway. Service and feeders. The service and feeders shall be sized in accordance with the product ratings, unless the overall rating of the installation can be limited through controls as permitted by 625.42A or B. All right, so A and B. So A is an energy management system. So let's say that I'm not employing an energy management system. All I got is I've got a Tesla or whatever vehicle charger, and there's a dial on the front that says 32, 40, 48, 64, 80. And there might be intermittent steps in between. So I got all of these options on what I want this EV charger to draw. And I know I can't go greater than 32, so I'm going to dial it down to 32, which is an EVSE with adjustable settings, and that is 625.42 Bravo B. I'm like, thank God, here we go. I'm walking, you gotta imagine me. I'm with somebody on the phone, and I'm walking them through this. And they're going, oh, this is great. So then I get down to EVSE with restricted access to an ampere adjustment means complying with 750.30 Charlie. 750.30 Charlie. So let's go to 750, and 750 is your energy management. So I'm sitting there thinking, well, I'm not in A. I'm not in 625.42A, which is energy management systems. I'm in B, just an EVSE with an adjustable setting. So why is it sending me to an energy management article, 750.30C? So I go to 750.30C. And 750.30C is called load management. And C is capacity of branch circuit feeder or service. So I go, all right, so it says an energy management system shall not cause a branch circuit feeder or service to be overloaded. But I'm not in 625.42A, which is the energy management system. I'm in 625.42B, EVSE with adjustable settings. So it says if an EMS is used, well, which it's not, I'm not using an EMS. And it says 750.30C1 through C4 shall apply. C1 is a current set point, a single value equal to the maximum value. A system malfunction, the EMS has to use monitoring and controls to automatically cease current flow upon malfunction. And then 3 is settings, adjustable settings. So now I'm like, okay, this makes sense. So the requirements that are in 3 are very similar to what we have in 240. If you go to 240.6 standard, remember it says local restricted access, adjustable trip circuit breakers, well, you know, located behind or removable and sealable covers, located behind bolted equipment closure doors, all that good stuff. So the language that's in 750.30 Charlie 3 makes sense and align, in my opinion, with what's in 625.42B, because the first sentence says EVSE with restricted access to an ampere adjusting means complying with 750.30 Charlie. So we went around. So this was the point of discussion. So what I learned from the individual was that, well, this wasn't even their issue. This wasn't their issue. His issue wasn't what I was looking at with 30C, but when I started reading it, his comment was, "Oh my, this opens up all other different types of requirements because it references Charlie, and now you've got to have the current set point issues, you've got system malfunction concerns, you've got the marking, the equipment that supplies the branch circuit feeder or service shall be field marked with the following information, blah, 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 blah." And so everything in C applies when you reference C in this article, in this section. So I made some phone calls, and I found out that the reference is incorrect. It should have just said C3. After all of the gnashing of teeth or gnawing of, I don't know what you call that. After all of that, I was like, ah! The section's wrong reference. So I'm okay. After I got the clarity, I talked to the chair of panel, was it 12? And Robert from Omaha. Excellent. Thanks for joining. Right, the adjustable settings have to be behind locked doors, sealable covers, etc. It could be just, that's what I said, Ryan. I said just point to 240.6. Don't go to 750, which is an energy management article. Go to 240.6. If this is no different than what we do with circuit breakers when I adjust the circuit breaker down to a smaller ampacity of a conductor. Okay, now remember, this wasn't even his issue. Okay, so I stumbled on this one. I'll tell you what his issue is here in a second. So I stumbled on that one, and I said, okay, so I called Joe Bablow, the chair of the code panel 12, And I talked to a couple other individuals, and I'm like, okay, I feel very comfortable that that should say 750.30 Charlie. But to your point, Ryan, it should say 240.6 C, 240.6 Charlie. A circuit breaker that has restricted access to the adjustable means shall be permitted to have an ampere rating that is equal to adjusted, and we should say any of the means listed. Now, there's 4 means in 240.6 Charlie. Let's look at 750. 750 says located behind, there's 5 options. Ooh, 5. Ryan, 5. So, you have located behind removable and sealable covers. Located behind removable and sealable covers, so that's the same in both. Located behind a cover or door that requires the use of a tool to open. That's in 750. 240 says located behind bolted equipment enclosure doors. Located behind locked doors accessible only to qualified persons. Located behind a cover or door that requires a use. So, located behind a door or cover that requires the use of a tool to open. Located behind bolted equipment enclosure doors. So we don't say the tool. So that's I sort of like the 750 language better. Located behind locked doors accessible only to qualified personnel. Located behind locked doors accessible only to qualified personnel. That's the same. Number 4 is password protected with password accessible only to qualified personnel. Password protected with password accessible only to qualified personnel. That's the same in both. And then the kicker, the additional in 750.30C is software that is password protected access to the adjusting means accessible to qualified person. Password protected. Software that has password protected access. So I guess there's another method for just software. So it should say C3. Section 625.42b only refers to the restricted access needing to comply with it. Well, so it does. It's not very clear. So that was my issue, Ryan. I was looking, and it doesn't say with the restricted access. It just says the EVSE shall electric vehicle charging load shall be considered to be EVSE with restricted access to an ampere adjustment means complying with 750.30C. It should say 750.30C3 because C3 is the settings, and that's what you're focused on, not everything else. All right, so that was the first. So that was like one of my little tangents, right? So I went off of that tangent, but we came back around. The Joe Babylon crew, I believe they're going to fix that. Okay, so it probably is better to go to that specific section in 750. Now, here was the area that was of question. If adjustments have an impact on the rating label, those changes shall be in accordance with manufacturer's instructions, and the adjusting rating shall appear on the rating label with sufficient durability to withstand the environment involved. So the adjusted rating has to appear on the rating label. So then the question was, how do you do that? Do I remember, as a manufacturer, I ship it from the field with a rating label. If you can't modify that label in the field. So the question is, how do I get that done? So I looked and I did some homework. Let me open show an enclosed folder, and I didn't put it there. I did some homework. Let me see if I have it in my pictures. Do I have, oh wait, do I have it in my Word document? I believe that I do. Yes, I do. All right. I have Exhibit A. I called it Exhibit A. This is like one of those things, Ryan, that I'm like, how do I How do I get this done? So I'm going to do this. I'm going to show this. So when in doubt, when you're trying to figure out this discussion, so I went, I figured, what other industry does this? Okay, fill in the blank on the labels like it's done in signs. Here's another industry that does something similar. And this is a HVAC equipment. So, in the HVAC equipment, you'll notice in this label, it says for field installed electric heaters, apply electrical information plate supplied with the heater in this block. And so this installation, they applied the information plate over the place indicated on the door rating, but they put it in the wrong spot. They just added it. So this label was supposed to be located here to replace everything that is in that label with what was added. Now, here's the thing, Ryan. You don't do this in I'll argue that you don't do this in transfer switches. And here's why. In transfer switches, the short circuit current rating, I put a recipe. It's just like a panel board. We do it on a panel board, right? I mark the panel board with a recipe. And I tell you, if you have these overcurrent devices installed and they're all 10K or they're all 22K, then you have a 22K panel board. In a transfer switch, we tell you when this is upstream, when that is upstream. But we don't change the label based upon what we have upstream. The label is the label. We have to read it. We have to go, okay, if I have a current limiting fuse of this size or smaller upstream, it's 200,000 amp short circuit current rating. Then I got to go check to see if that's the fuse I have. We don't have a field marking of the short circuit current rating. We have the field marking of available fault currents. I'm sitting here saying we don't, and I'm waiting for you to go, oh, yes, we do. But so, and even if it's software modified, Ryan, I've got to change the label. So when I look at the HVAC industry, I call it Exhibit A. This label is supposed to be over here, and then that's your new rating. Oh, yes, we do. 700. I knew it when I was saying it, when I was freaking saying it. Hold on. I got to read that. You're funny, man. That is hilarious. You know, if there's anything in codes and standards, never say never. And never say we don't. 700.5F. The short circuit current rating of the transfer equipment, based on the specific overcurrent protected device and settings protected by the transfer equipment, shall be field marked on the exterior. Oh, that is so freaking awesome. That is beautiful. And that must have been added. Hold on. When was that added? I'm going to grab the 2020 code book. Is this a 2020 change? 700.5F. Oh, man. 700.5F. You know what's funny, Ryan? Yeah, so that's the short circuit current rating of the shall be based on the transfer equipment shall be field marked. Oh my God, I'm going to go 17. I'm going 17. 700.5. I should have known this. I feel like an idiot. It was new in the 17 code. Shall be field marked on the exterior of the transfer equipment. That's when it happened. Well, see, there's my problem, Ryan. There's my problem. It only happened within the last 9 years. Okay? So this was 9 years ago. Peer character doing a classic mic drop. You owe me $5 for that one, buddy. Dadgummit. All right, so I sit, corrected. Oh, hail, great Ryan. Thank you. Gosh, darn it. Man. All right, so because it doesn't specify in 625 how we do the marking. So let me ask you a question. We got some inspectors on here. What if I used a Sharpie? What if the manufacturer said, put a little square box and said, write in the amperes of the set points in your software that you set here, and then this is the rating, and you use a Sharpie. Is there any prohibition on using a Sharpie? This is a Papermate red pen. Free beer. Thanks, Ryan. So could I use a Sharpie? Could I do a field marking like that? So, but it does say it has to be of sufficient durability, right? So I would go back to maybe a Sharpie is not a good thing. You know what I like? What I like, you're gonna find me crazy, but when you're pumping gas, you go to a gas station and you'll see the last inspected date. And you'll see a little sticker and it has a bunch of dates on it, and there's a hole punched in the date when they did the inspection. I like the hole punch thing. I really do. I think it would be really cool if you had a label that said all the different ratings and you could put a punch next to the rating. Yes, so Steve Fromming, sufficient for the environment. What's to say that a Sharpie is not sufficient for the environment? It's indoors. My EV charger is in my garage. Is it sufficient for the environment? Do you think I could walk over, wet my thumb, and scrub it and wipe it off? Maybe. But is it sufficient for the environment? I had one inspector tell me that they use Sharpies every day on some of this HVAC equipment to mark the ampacity or the load based upon whatever it is they're installing. This is kind of nice. I like the way this manufacturer did it, because they have this label which has, if you buy an added heating element and you install it, you take this and you put this right over this area. I sort of like that. But apparently, so the question is, from an EVSE piece of equipment, you need, well, it's not a question, it's a point. You need to mark it. You need, whatever the adjustment setting is, whether you do it via software or whatever it is, you need to mark the nameplate, because it says nameplate. It said the adjusted rating shall appear on the rating label. The rating label. So you would have, if the rating, so in any case, you really, is a separate, like if I say, well, it's on a display. Let's say that my EV charger has a display. I'm looking at my Tesla or whatever it is. But here's the thing, Ryan. You may have a label maker, but you can't make a label and add it and say, look, the setting is this, and put it somewhere on the unit where it's visible. That wouldn't meet the code, because the code says that shall appear on the rating label. And if the rating label doesn't give you any room and you put it somewhere else, that doesn't meet the code. So that was the question. So in like in the case of this guy here, with this HVAC equipment, and I don't know what the HVAC. I haven't looked up the section in the right article here, but the manufacturer's instruction says to install that additional label over right on the label on the left. On the label on the left. And so you just can't make a label and stick it on there. It has to be on the rating label. So in my opinion, the manufacturer has to think about that. The manufacturer's going to have to give you a spot like they did with this HVAC label. Now, it's up to us to follow the rules, and apparently this installation didn't. They put the rating label over the diagram, and they didn't put it where the one label says to where to put it, and then the other. So insert shapes. So right here, so this label right here, that label right there, I'm going to give it a red edge. We'll give it a nice thick. So that label, Control C, Control V, is supposed to go right here. And replace the rating information that's on the rating label. So having your little label maker and putting it somewhere on there that this is 60 amps ain't gonna cut it. In my opinion, based upon the language as it stands in the 2023 code, it's not very clear. But it is clear that it has to be on the rating label. What about dial a date? That sounds like a dating service. Not all label ink is sunlight. Oh, that's there you go. That's a good point. You have sunlight. You have the weather, the rain. But if it's in my garage, I don't have to worry about sunlight. I don't have to worry about rain. I don't have to worry about weather. Why can't I use a Sharpie? As long as there's a spot. I wish the durability and the labeling was clear. But in this case here, so where we ended up. Where we ended up was that, look, you have to put you have to put the rating in a specific location. It's got to be on the rating label. How you get that done is between you, the inspector, and the manufacturer. So you can't cover, if there's no room on this rating label to add the actual rating, read the instructions. The instructions should address it. But you're going to have to work with the inspector if it's, I think it just needs to be evident. That's all. All we want is to make sure that people know this is 32 amps continuous. Don't put it on a smaller conductor. And if it's because if it can go to 80 amps, well, here's the other issue. If I put it on a 40 amp circuit and I turn it up to 80, whoopee ding ding. Right? I'll trip the breaker. And then I'll go, oh, I shouldn't have turned it up to 80 amps. As long as, so, as long as I'm protecting the conductor at my continuous rating, then I'm good to go. The only issue you'll have is nuisance tripping because you'll draw more current than the circuit can handle. Anyway, so that was the first one. So two things I learned there. One, I have to go put the rating. I have to put the rating on the label. I've got to think about ways to get that done. Depending upon the EV charging equipment that I get, work with the inspector, work with your AHJ, work with the manufacturer, figure out where that label has to go. You need to figure out how to create it. If the manufacturer doesn't give it to you, you're going to need to figure out how to create a label that's durable. In my opinion, I wouldn't use a Sharpie, right? Or a marker or any magic markers or things like that. Make your work look professional and durable and lasting. Check the ampacity of the conductor, check the ampere rating of the breaker. Make sure all of that's in line and we're good to go. And the second thing is that if it's adjustable, follow the methods identified in 750.30 Charlie 5. 5. I think it's 5. 750.30 Charlie. 750. Oh gosh. 750.30 Charlie 3. All right. Can you call the manufacturer after determining the setting and have them make a label? Oh, okay. So here's the other issue. Now remember, this is UL listed equipment. You can't replace labels in the field. Just can't do it. I mean, honestly, if for example, let's say that this label on the left, this label has the UL mark, the whole bit. I'm not reshipping that label. I'm not making a new label in this case. I can't. And if I did, and you were going to apply it in the field, I need a UL inspector there. Not a UL inspector. I need a field evaluation body there. An FEB. Because I've got to make sure I'm putting the right label on that equipment. Because all of the rating information's on there. Catalog number, voltages. There's a lot of information on that label. So Robert, it would be hard pressed to legally send a label to that piece of equipment out in the field. Now you could, because you all label, everything's on there, you could have the supplemental labels like the HVAC industry does. And Ryan pointed out, what did he point out? It was before the free beer. You know what, Ryan? So the requirement in 700.5F doesn't say the SCCR has to be on the rating label. That's another difference. You have more restrictions when I tell you it has to be on the rating label. And it's not a label that I can ship. So, all right. Okay, so what was next? All right, so that was my EVSE. That's the so a couple things. One, I can have adjustable settings. I can use an energy management system, but in my opinion, most of these are going to have set points. You're going to program the set point. You've got to make sure you have a lockable cover. However means, whatever you do, you can adjust it to a lower value. Put it on a smaller conductor with a smaller breaker, and I think that's more valuable in an existing installation. Make sense? That's what I meant. A supplemental label in addition to the, yes, you could. So, and this, Robert, is what I was thinking would be kind of cool if you had all the different options and just said, hey, put a check mark next to the one it is. Or hole punch it out and then paste it on the equipment. And if the manufacturer would do something like the HVAC industry does, give you a little spot to put that sticker on. There's a lot of different ways to get that done. And I think you can get creative because It's not as clearly defined as it could or should be, in my humble opinion. But you know what? I think a lot of people love to work in the gray area. I really do. All right, so that is my EV. You know what? I had three. I had selective coordination, but there was a third one, and I, for the life of me, didn't think I needed to write it down. And that's what I get. All right, so zone selective interlocking. Let's talk zone selective interlocking. Zone selective interlocking, ZSI. So zone selective interlocking. First, let's do this. So ZSI and selective coordination. Third one is 70p. 70p. I got to create a committee. We're going to do this. Robert, or put a 50 amp range receptacle there and have no EV appliance on site for the, ooh. Yeah. I'm with you, Stephen. So we need a 70 pizza, 70p for a pizza. I am going to start, you know, man, if I have so much to do. I don't have time to craft language, but I would love to. And I just might, just for giggles. All right, so let's do this. Let's get into these two topics. So here's what the individual that I heard on the video say, that what he uses is zone selective interlocking to achieve his selective coordination requirements. That's the statement. And you know, for me, that's like nails over a chalkboard. I don't know why I get so irritated with it. I don't know. I think it's because I've heard it so often, and I've heard it from some very, very smart individuals. So, selective coordination first. What is selective coordination? I have a time current characteristic curve. I have amps along the bottom. I have time up the side. And we draw curves. So first off, let's do this. Let's say that I have this going on, right? And if I have a fault here, which breaker, and we'll call this A, B, C. If I have a fault downstream of breaker C, what do I want to open? Breaker C. I don't want B to open. I don't want A to open. If I have a fault in this panel board here, I want breaker B to open. I don't want breaker A to open, because remember, I have other breakers, right? Right, Robert. So I want the device closest to the fault to open. That is the fundamental principle of selective coordination. So how do I do that? Let me get rid of this. I short circuit is equal to 10K. Let's say that that fault current right there is 10,000 amps. Then what I need to do is I need to compare the time current characteristic curves of all three of those, because, why? I'm glad you asked, Robert. Because my fault current that flows is going to be 10,000 amps. Now, I don't have a transformer in there. If I have a transformer, remember, transformers do not cease to do their job. When there's a fault, it will. The laws of physics. Christmas in October. The laws of physics do not cease to exist on Ryan Jackson's desk when you have a fault in the system and there's a transformer in there. I don't have a transformer right now. Hey, Juan Guardado. Juan, great to see you. Welcome. California in the house. You're the man, the legend. So 10,000 amps is going to flow through each of those devices. I need to compare fault current with the performance criteria of the circuit breakers, and what do we use to understand how a circuit breaker responds to current? We use the time current characteristic curve, TCC curve. Remember, it's not time current curve. That's a shortcut. That's lazy. We don't tolerate laziness on this channel. It's time current characteristic curve. Don't forget the word characteristic. So, device C just might look, whoa, let's draw device C in blue. Here's device C. Here is device B. And here is right. So this is C, B, A. Okay. So those are your three curves. And if you are not sure what the heck's going on, now what do these curves tell us? Okay, so a time current characteristic curve Brandon Klingeman. Yes, this is a calibrated tool by the National Laboratories in Los Alamos. Calibrated this 10 seconds before I used it. All right, so I have device C is the furthest down. So, okay, so we'll say, I don't know, we'll say this is 0 amps. And we'll say this is 0.01 seconds. And this is 0.1 seconds. And blah, 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 all the way up. And this is, and let's say that this is, I don't know, 30 amps. This instantaneous is probably 3,000 amps. And I'm saying that, okay, now you gotta be careful. What I said was, on a standard thermomagnetic circuit breaker, do this. Let me show you something. I'm gonna call up, I'm gonna do this. I'm gonna do Eaton circuit breakers, TCC curve. Time current characteristic curves. I'm gonna go to molded case circuit breakers. What's the power defense? I want do this. Let's do this. All right, so this is our GHB. This is, you can get a 30 amp curve. So this is page 6. I'm going to go to page 6. Page 6. 9876. All right, so this is a thermomagnetic circuit breaker. Time, oh, lazy. Lazy, right there. That is lazy. Time current curve. Lazy. Lazy. Whoever drew this curve is lazy. All right, so this is, now these are funny because this is current in amps, but 30 amp rating. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So 10, 20, 30. So 30 amps right in here. 10, 20, wait. 10, 20, 30. So there's your 30 amps, long time pickup, all right? If I come down 30 amps, where's the instantaneous? Oh, this is actually less. So that's 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000. So it picks up less. I don't think it's it's definitely not adjustable. Let's take a look. Any notes? So for a 30 amp breaker, 100, 200, 300, 400, 500. What was I talking? I said 10,000. It's usually 10 times. 10 times 30 is 300, not 3,000. 10 times 30 is 300 amps. I would have expected this to be somewhere around 300, but it's actually higher. So you're getting into the instantaneous around 200, 300, 100, 200, 300, 400, about 500 amps. So my instantaneous is around 500 amps. So, and that, well, yeah, so look at that, I drew that, 3,000. So this is around 500 amps. And I said my available fault current's 10,000. So if that's 500, and then let's see, I don't know, maybe device B, anytime you see that I call it a beer gut, right? Supercalifragilisticexpialidocious. Don't talk at all. That's right. So anytime you see that beer gut like that, right in here, is what I'm talking about, that's very indicative of a standard thermomagnetic circuit breaker. Anytime you see straight lines like that, that is an electronic trip unit. So instantaneous on this circuit breaker is up closer to 100, 200, 300, 400, 500 amps at the beginning of the pickup, right? Let's take a look at single pole 40 amp. Look at this is a single pole 40 ampere breaker. So 40 amps, 10, 20, 30, 40. That's where it starts to pick up. Instantaneous, a lot of people would say 10 times, so you would think about 400 amps. 100, 200, 300, 400, 500. So the instantaneous pickup, so this is what it tells you. The mechanism, the instantaneous mechanism is the same in this circuit breaker for the 40 amp, the 35 amp, the 30 amp, the 25 amp. Now let's look at the 20 amp circuit. 20 amp, 100, 200, 300, 400. Different. Look at the 25. 100, 200, 300, 400, 500. So it's the 25 amp breaker where the design for this breaker apparently uses the same instantaneous. They changed the mechanism, the internal mechanism. Now the instantaneous is picking up at 500 amps. So let's go back to the 20 amps. Let's go to 15. 15 amps, 100, 200, 300, 400. And there's no 10 amp. Okay, so for this breaker, one mechanism in the instantaneous, and they're just moving the long time pickup. So thermally inside, the thermal is changing. So it's the same mechanism instantaneous for the 15 and the 20. The 25, the instantaneous moves up to 500 amps pickup. It's the same for 35 amps, 40 amps. Let's look at the 45. 1, 2, 3, 4, 5. Same. Let's look at the 50 amp. 1, 2, 3, 4, 5. Same. Let's look at the 60 amp. 1, 2, 3, 4, 5. Same. Let's look at the 70 amp. Boom. Different mechanism. So this is a 70 amp breaker. Now you would think 10 times 70 is what? 700? 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000. This is 2,000, so around maybe 1,200 amps is where you're picking up on a 70 amp breaker. That's a lot more than just 10 times. So that's why I always tell people, be cautious. They like to use the 10-time multiplier. They'll say, oh, instantaneous is 10 times. Where you get in trouble is if you're trying to rely on that rule of thumb for arc flash reduction or anything like that. Don't rely on that stuff for any arc flash reduction. If you're picking safety, personal protective equipment, don't do it. Don't rely on those little rules of thumb. 30 amp long time pickup rating that doesn't open instantaneously until 500 amps. Are these designed specifically for motors? No, they're a standard multi-case circuit breaker. Remember, there is no control over the instantaneous. Now the reason, so 30 amp, now let's go to the 500. 1, 2, 3, 4, 5. So here is a 60 amp. What's 10 times 60? 600. You would think that the instantaneous on a 60 amp breaker would pick up around 600, but no, it's 500. So it's a little less, Ryan. So the reason the mechanisms are that way is because the manufacturer in this case is using the same mechanism for instantaneous on all of those circuit breakers. It's the same pickup. Remember, it's a dumb device. It's a mechanical device. You got the clapper going on, right? You've got, let me show you something. You've got, where is it? Here. So, can't really see it. Here we go. Here we go. So, you've got, all right. I need a pen. I need a pen. Now we're into Breakers 101. And I don't care. I don't have a pen, and that won't fit. Oh, here we go. Does that fit? Whoa. I scared myself. Oh my gosh. Now that was freaking funny. I was like, whoa. Oh shoot. I need here we go. Here. Perfect. I got a screwdriver. All right, so how am I going to do this? All right, we're moving on the fly. Moving on the fly, Ryan. All right. Whoa, crapolas. All right, let's do this. All right, so all right, here's what we got going on. This is a thermomagnetic circuit breaker. When I say the instantaneous on the instantaneous versus thermal, okay? So I'm going to try to show you the instantaneous and the thermal on here. This is tough. This is what goes in on the, this is what goes in on the bus. Over here is where we have the screw where the conductor comes in. So if you follow from this screw, goes up along this line, I gotta get my glasses on, goes up this way, over and down through this mechanism right here. So this is your bimetal. Your bimetal is right in here. When I talk about the clapper, this piece, that little piece right here that I'm touching, that is going to be pulled in when the current that comes through here, down through this mechanism, down through the contacts and down to the bus. When that current gets hot and gets this bimetal hot enough, this is going to bend. This bimetal bends, and then if it's really high, this piece right here will be sucked in like this. How do I do this? Let's try to do it this way. I'm going to move the instantaneous in. I don't know if I can do that. Okay, you see how that moves right there. That movement releases the latch. So when I move this in, it trips the breaker. So this mechanism, the bimetal will be different for some, but the magnetic portion will be the same for some of these breakers. So that is why you'll see the instantaneous pickup. You'll see the long time pickup way over there on the left. Like you said, that 30 amp breaker, the long time picks up over here, but the instantaneous is way over to the right. And that's because I'm utilizing one mechanism for a series of circuit breakers. UL 489 does not require me to have an instantaneous at all. Right? I put it in to protect the breaker itself. So the I used to have my sample anyway. So I will create a series of products, and I'll move that long time pickup left and right, and the instantaneous may be way over there because that's the mechanism I used. And I'm just changing the bimetal for the overload. So between the 25 amp up to the 70 amp, they are identical, right? Identical. Yes. So now if I go back to this, so I'll pick different breakers for each of these. And then what I do is I compare, if that's 500 amps and I'm at 10,000, if 10,000 amps is right here on this curve, I'll draw it in red and orange. If this is 10,000 amps, what I know from these curves is that definitely device C is going to open because I'm way to the right. I'm into the instantaneous region of that curve. I also know that I'm probably going to trip device B, but it really depends on how current limiting device C really is. There is nothing on this time current characteristic curve that tells me what B will do, if it will hold its contacts closed while C opens or not. So what do? Manufacturers publish tables. And we'll say, okay, look, I tested that breaker downstream of whatever model that breaker is, and I'll publish a number. They're called the selective coordination tables. And if I go to Eaton selective coordination tables, all of this is related to this ZSI issue, believe me. And I go to selective coordination tables, you'll see a table in here. Let me find it. Here it is. So what this tells me is I have my downstream breaker, my load side breaker down the left. So if I have a 15 amp BAB, 15 amp downstream of a PXR PDG-3 PXR trip unit for a G, K, or an M frame, I can, and a 125 amp frame that's adjustable down to 45 amps, anything over 3,000 amps, I'm going to trip both breakers. Tested it. I know. I just know. We tested it. So I can have a 15 amp breaker, anything over 3,000 amps. So if this upstream breaker, if this breaker B was one of those, I'm at 10,000 amps, I know for a fact they're going to trip. In fact, if I had a 30 amp, so it's 2,500 amps for a 30 amp breaker right here. So if I have a PDG 345, now if I want to make it, so that would be 2,500 amps, and I would have to address the issue, and I can do that various ways. Yes. So Brian, so here's the issue. And I was surprised too, because it has amps, okay? This is current in amps, but that's not typically how we do things. You got to be very careful. Let's go to an FD frame. And let's take a look at how different curves are represented. Look at this one. Now this is an electronic trip unit. This is current in multiples of IR. So not all trip curves are going to be as nice as that GHB as this is in current in amps. They're not all the same. There's no standards on how we publish trip curves. Okay? No standards. So every manufacturer is going to do things a little differently. For the most part, I would say there's a lot of consistencies. But just keep in mind, it's not going to always be that beautiful. So now, what do I know? That if I have 10,000 amps, they're both going to trip. If let's say that I was the gentleman who said, I use zone selective interlocking. If this is my scenario, and you know, we know what B and C is. If I zone selectively interlock these two together, now what does ZSI do? Let's talk about zone selective interlocking. Here's what we do. We have breaker A, and we have breaker B. On the side of the circuit breaker, we're going to have a wire. And I think this is the way they draw it. It's a twisted pair. It's not a twisted shielded pair. It's just a twisted pair. And there will be a constant, it will be a voltage. So, and let's assume that both of these are connected together. Now, in a switchboard or switchgear, I might have multiple breakers downstream, right? I might have multiple breakers downstream doing the same thing. A, B, and C. So in this case, A and B and A and C are zone selectively interlocked. What does that mean? Here's what it means, and I'll tell you where we run into a problem. It's how some people teach it. And this is how they typically teach it. You know why I know? Because I used to teach it this way until I realized I was causing a problem. I was confusing people. You try to simplify things, and Ryan, you probably know this. What platform is everybody on when they are interacting with you, Mr. Facebook user? They're over on my YouTube channel. You got to get over on YouTube. I don't know where you're at. Why are you over there on Facebook? What you doing? YouTube, www.youtube.com/c/Thomas Dimitrovich or /at TD Unplugged. Look, here's what you do. Let me show you something. You go to www.youtube.com/@TD Unplugged and hit enter, and boom, there you are. If you go to live, you'll see that I am right here. All right. So I know you're out there on YouTube, and there's some people probably watching on LinkedIn or out there on, and I've got a few places on Facebook, but that's where I'm at. And if you go to thomasdimitrovich.com, just my full name, thomasdimitrovich.com, you'll go out to my website, and you can click on my live stream, go straight to there. You can connect with me on LinkedIn, Facebook. I got to change the bird to the X, and then Instagram. And we're not streaming on Instagram right now, but anyway, that's where they're at. All right, so I have these breakers zone selectively interlocked, and what I used to say was I would say for a fault downstream of B, I would go, all right, so what happens for a fault downstream of B? You've got this current that flows through breaker A and through B, and it goes to the fault. Both breaker A and breaker B see the fault. And if it's large enough above the short time pickup of each of those breakers, and this is how this is how I used to teach it. Breaker B tells breaker A, I got this. Hold your contacts closed while I clear the device or clear the fault. And then breaker B opens and clears the fault. And that is a oversimplification and it's misinformation. And I'll tell you why. Because here's what happens. When you first install the device, let's just say that this is what's going on. I've got a device B and a device C. And let's say, for example, device B, let's say device B, I'm going to erase a portion of this, is not thermomagnetic. Let's say that it's an electronic trip unit. Okay, that's how we know it's an electronic trip unit, because it's very straight lines. If I have this scenario and I have B and C zone selectively interlocked together, and my fault current is above the instantaneous of both of those breakers, when I have this fault downstream and that fault current flows through both of those breakers, I'm in the instantaneous region of both breakers. I don't care if you have zone selective interlocking. They're both going to open. You have a high fault current. You're in the instantaneous region of both. They are both opening, regardless of what you do with zone selective interlocking. But here's how zone selective interlocking really works. When that fault current goes down through both breakers, breaker B and breaker A both see the fault. Breaker B puts a voltage on that signal, on that wire. When breaker A sees it, now breaker A sees it go above a value, it sees the current. The first thing it does is it looks at this terminal right here. And it says, am I getting a signal from downstream? Which what it means is the breaker downstream sees the fault too, because the breaker downstream, when you went above the set point, it put a voltage signal. I'm like, I don't care what the voltage is. Say it's 24 volts DC, 5 volts DC. Every manufacturer is going to be a little different. I'm putting a voltage signal on this wire. Breaker A says, I see a fault. First, it's high enough. Hey, you're triggering me. I'm looking down at that terminal. If I see voltage there, then what it does is it goes by however you programmed it. So if your trip curve up here says that you need to wait anywhere from 10 to 20 seconds for that fault to clear, because there's zone selective interlocking, because B is putting a voltage on there, when A sees that fault, device A is going to go by how you programmed it. If you have two devices, if B did this and then up, well, device B is going to trip first, regardless of zone selective interlocking, because it's going to go how you programmed it or how you didn't program it. That's the issue that we have. These devices ship on minimum settings. So if you don't set for coordination in these regions, in these regions here, if you don't set those and program those trip curves, you can have a nuisance trip, a lack of selective coordination, because you did not do your work in A, doing the evaluation on paper or on the TCC and some software, and B, you didn't change the settings in the field. James, we are all good, buddy. Rossman. So that's how this would. Now, if I have a fault here, okay, let's forget about the fault down here. Let's say I have a fault in between the breakers on the bus. Device B doesn't see any current passing through it because the current doesn't go all the way down, right? Where does the current stop? Right there. Now your current goes to the bus. Only device A sees it. When device A sees the fault, it's going to look at those terminals again. Look at these terminals. If it doesn't see a voltage signal from either B or C, it ignores your set points and goes instantaneously. That's what it does. It protects very fast faults that occur within the zone of protection. But remember, you have to program that device A. If you don't set the long time pickup, long time delay, short time pickup, short time delay, and there is overlap, device A could trip. It doesn't automatically adjust the TCC curves, pushing out delays. No, whatever your set point is. So, zone selective interlocking doesn't get you selective coordination. If I have a fault current passing through both of those and it's 10,000 amps, and my instantaneous pickup here is at 3K, and my instantaneous pickup here is at 500 amps, they're both opening. End of story. And I have tables to prove it. So zone selective interlocking has absolutely zero to do with selective coordination. Do you know what zone selective interlocking is good for? If you are trying to protect the integrity of the equipment or faults that occur internal to the equipment, zone selective interlocking will make sure that if you have an internal fault, that upstream device goes without an intentional delay, period. That's what it does. So zone selective interlocking is there for arc flash reduction. It's not there for selective coordination at all. It's not what its goal is. Its goal is for reducing equipment damage. And I hesitate with arc flash reduction. And here's why. Here's why. I'm going to go back and let's say we go back to this, right? And what do we do in a piece of equipment? We have a connection point here. We have a connection point here, and here, and here, right? If I have a fault on the load side of this device, this is say A, B, C, and D. I'm getting there, Ryan. I'm getting there. This is my issue with 24087 and 24067. If I have a fault here, and let's say device B has a 30 cycle delay, the zone selectively interlock between these devices doesn't help me. Because I'm outside of the zone of protection. Remember, ZSI has a zone of protection. Differential relaying, talk differential. I have the same scenario. Right? I have the same scenario. If I use differential, how does differential work? I put a CT. If I put the CT there, and I put a CT there, and I put a CT there. Let's say this is a relay. And that relay reads the Gesundtas and the Gesaltas. At least the lugs, if I'm on the conductor, now I have much better protection. Because now that termination and this termination, and if the relay trips an upstream breaker, I'm even better. Now I have very good, much more complete protection inside the house. Hey, Mr. E is finally in the house. David Engelhardt, thank you for joining us. So, Ryan Jackson, as it relates to 24087, workers in equipment A are protected, but those in B's equipment are not. A and B. Well, remember, this is all in the same equipment, Ryan. This is all in, now I can daisy chain. Okay, so if I zone, say I go back to, say this is zone selective interlock. If I feed here, let's say I have another piece of equipment. Okay, let's say this is another piece of equipment. And I zone selectively interlock these two. Yes, I'm working in the equipment. I'm within the zone of protection. The zone of protection, Ryan, if I look at, say, two breakers, let's just go back to two simple breakers that are zone selectively interlocked. My zone of protection is right here. Hold on. My zone of protection is right here. If I have a fault here, I go at the clearing time of this device, B. If I have a fault anywhere downstream of the lugs on the downstream device, I am outside of the zone of protection. I am at the mercy of whatever the settings are in device B. If I am on the line side or on the bus or on the load side of that device A, then I'm in the zone of protection. Device A will trip without an intentional delay, reducing your protection. If I have a fault on the line side of device A, I'm outside of the zone of protection. Device A doesn't even know it happened. So in a piece of a panel board like this that's zone selectively interlocked, my zone of protection is here, here, here. That's my zone of protection. I'm protecting and we've used this when I first started with Eaton. I started with Eaton in 1996, and I started on a help desk. I learned about zone selective interlocking back then. That was in 1996, and it wasn't new. So we've had zone selective interlocking, but you know what? The petrochem industry, many large industrials would buy equipment with zone selective interlocking to prevent a lot of damage to the equipment due to internal failures. Groundhogs getting in, mice getting in, any type of rodent, water penetration, whatever it is. Zone selective interlocking will provide the protection of the bus structure and the bus inside that equipment, limits your damage, easier to get back in service, faster. As an electrical worker, I don't know that I would rely on it. Jacob Riddle, this is where the cool cats are, buddy. Come on. This is Friday night, and we ain't got no money, so we try to work for Ryan Jackson giving us beer money online. Still don't know how the heck he figured out how to do that. So working in that switchgear on the load side of B's terminals, the worker does not experience reduced. That is correct, Ryan. You're at the mercy of the clearing time of B. That's my fundamental issue with 24087 and 24067. In my opinion, the only thing that should be in 24087 and 24067 is the arc reduction maintenance switch. And arc quencher, I could argue the arc quencher could be in there. It gives you much more comprehensive. You might convince me, Rabbit, to support the differential relaying for the fact that the CTs are where they're at. Yes. So, in my opinion, this is where my head's at. I'm telling you, this is where my head is at, Ryan. 23095, ground fault protection of equipment. Why did that go in the code? 230, I'm getting on my soapbox. I'll be careful here. I'm getting on my soapbox. All right? 23095. And remember, anything I say right here, coming out, what comes out of here started up here, and it's all from the heart. All right? All from the heart. Why isn't it working? Must have turned it off. So anyway, in my opinion, the ground fault protection of equipment found in 23095 went in 1971. Why did we put GFPE in service entrance equipment in 1971? Was it to solve a problem in lighting equipment downstream? No. Was it to solve a problem, a ground fault problems in motor loads? No. It was there because various things occurred in the industry. And Ryan, you probably heard me get on my soapbox, but I'm going to tell you this, I researched this. Here's why we put ground fault protection of equipment in service entrance equipment. 1971, think about before 1971, the 40s, the 50s, the 60s. We had a lot of ungrounded Delta systems. They were Delta, they were ungrounded Delta, they were 208 volts, and they were Average service was 600 amps. Okay? What happened? Someone somewhere said, hey, you know, Joey Two Shoes down the street, his system is grounded. They grounded the corner delta, and now all of his voltages are in line. He doesn't have the voltage fluctuation issues. He doesn't have the transient voltage issues. He doesn't have all the problems associated with delta ungrounded systems. So what happened? They said, you know what? We're going to start doing corner grounded delta systems, or we're going to put this spider on the drawing and we're going to do a zigzag transformer and we're going to ground the system. And what does that do? That's like a boat. An ungrounded system is like a boat floating in the ocean. Your voltages go up and down. You're like a boat in the waves without an anchor. The moment you ground the system, now you're a boat anchored. And now you have a much more stable system. But the problem was, the first fault is no longer a gimme. That first fault is a doozy, right? It's big. So they went from ungrounded to grounded systems. Then they went from 208 volts to 480. Okay, higher voltage, more pressure. Then, I love this stuff. Then they went from an average of a 600 amp service up to 3,000 amp services. So the services got larger, the voltage got higher, they grounded the system. Perfect recipe for an arc flash event in service entrance equipment. So there were cases of service entrance equipments, they called them burn downs back then. There were arc flash events. I'll get to you, Jacob. So there were arc flash events happening at service entrance equipment. So at this time, think about it, 1970s or 60s into 1970, what was going on in our electrical industry? We were developing ground fault sensors. We were taking electronics. If you look at the history of computers and how computers went from filling a freaking room to now we have almost, you're close to integrated circuits and things of that nature. Now we can get it small enough, we can put them in relays. So we created ground fault protection of equipment. And if you look at all of the panel, you look at the IEEE documents. There are IEEE documents done by Dunkey Jacobs and testing that was done, where they showed, okay, faults inside of switchgear and whatnot, that ground fault protection of equipment could be a solution. What's the problem with ground fault protection of equipment? It looks way down into the system. So the second problem that we had with ground fault, once they put it as a requirement in service entrance equipment, okay, then they were like, well, how do I set this? Because my service entrance equipment is tripping on unbalanced currents and things like that. I'd get what looks like a ground fault, or I'll get temporary ground faults, whatever, taking out the service equipment. So then they started they bopped it up to 1200 amps pickup, and then up to a 1 second delay. Think about that from an arc flash event. What's 1 second in an arc flash event? So in any case, that's how we got 23095 in the code back in 1971. So fast forward to today, we have arc quenching technologies. I'm going to show you. I'm going to show you a video. Go back in time with me if you would. I'm going to show you a video of an arc flash, let me do quencher. Quench. I know I can, videos. Quencher, here we go. All right, here we go. You ready for this? So I gotta, dadgummit. Here we go. I said here we go 17 times, but I'm gonna say it one more time. Here we go. All right. This 85,000 amps, standard construction. Whoa. Whoa. Like it's a Joey, whoa! This is in slow motion. 85,000 amps, standard construction. There's nothing wrong with the installation. This is all per the code. It's UL listed product. There's no problem outside of causing something to happen, okay? This is arc quenching technology. Same exact scenario. Watch the slow motion. That is a active arc flash mitigation system. So, you buy a system like that and put it in your service entrance equipment, and you still have to buy ground fault protection of equipment. I get the sale. Cha-ching. But what value did you get out of ground fault protection of equipment with a 1-second delay when you've got technology that will give you that performance? And if I got the doors open and working in there, I get the same performance. But the code says 23095, gotta have GFPE. So that's the first one. The second one is if I put zone selective interlocking in. ZSI. Do I have ZSI? Yes. I've got a video. I think I got a video. I think I can. I think I can. I think I can. ZSI. Do I have a video? I don't know if I have a video. Let me look at videos. Search ZSI. No, I don't. I thought I did, but I don't. But in any case, zone selective interlocking can give me really great equipment level protection. Differential relaying. So in my opinion, Ryan, after all said and done, in my opinion, I think they should take zone selective interlocking out, move it over to 23095 as an exception to ground fault protection of equipment and service equipment. Make it an equipment-based requirement, not branch circuit feeder. Get rid of that crap. Make it a service, make service entrance equipment. You either are going to put ground fault protection of equipment in there, GFPE, or if you do zone selective interlocking, you don't need GFPE. If you do an arc quencher, you don't need GFPE. Right? So if you're putting technology in the equipment to address the integrity of the equipment for these types of events, which is the reason why I went in the freaking code in the beginning, why do you need to put GFPE in there? I think it should be an exception. And then get it out, get some of those out of 24087, because in my opinion, they don't work for the electrical worker. They're not there for arc flash reduction on how you would dress. Now, if I'm downstream of an arc reduction maintenance switch or an instantaneous or a current limiting fuse, amen, 7 days a week, twice on Sunday. I'm good to go from an electrical worker perspective. That's what arc flash reduction is, in my opinion, 24087 and 24067 is supposed to address. So now I'm off my soapbox, all right? So are you seeing folks using the arc quencher on new equipment or mainly new? Mainly new equipment. And the reason is, Ryan, is because you've got to put all those different light sensors in there in certain spots. I have not, now I'm not saying it hasn't happened, I have not personally been made aware of existing installations upgrading to arc quenchers. I'm not saying it's impossible. I'm just saying I am not personally aware of it. Jacob Riddle, thank you for coming to thanks for showing up, buddy. The ZSI wire recommended is 14 gauge, stranded tinned copper twisted pair. Twisted pair, remember I told you no shield. 600 volt insulation, 600 volts because where you're running it, right? 90 degrees C rated. Okay. Why is this not a requirement and just a recommendation if the conductor selection can negatively affect signal performance? Jacob, I look forward to your public input. That's all I can say. Right now, it's a part of the manufacturer's instructions. Could it work if you didn't use that? Yeah, maybe. You would have to run through the tests, but I don't disagree with you. And so here's the other thing. If we focused on 23095 for these types of technologies to provide protection of the equipment, of that specific equipment, now then you could put requirements like this. And the other issue I have, Jacob, is you would want to do a review of Schneider Electric, Square D, ABB, Siemens, and Eaton, and see, do they all use the same size conductors? I don't know the answer to that question. I do not know. I'd have to look through their installation instructions to determine whether or not it should be there. I got some money because I just got paid. How I wish I had someone to talk to. Robert, you're the man. Yes, so zone selective interlocking is there for equipment protection. It's not there for selective coordination. Absolutely nothing to do with it. Power Expert release PXR electronic chip units provide a new level of ZSI capability. Could you explain the new advancements in the PXR units? Yes. So the PXRs. So here's the other problem with zone selective interlocking. Oh man, I'm glad you're my straight man. You are my straight man. Let's do this. Let me show you something. So let's go. Whoa, I'm not even going to show you that picture. You know that over COVID, I completely shaved my head bald. Yes, I did. Completely shaved my head. All right, so now I'm going to go to library, and I am going to try to find a piece of equipment, a low voltage assembly. And I will show you the problem that most installations have when they employ zone selective interlocking, except for good old Eaton. Gosh. Here we go. I'm close. I'm close. All right. Here we go. Here we go. So, Mr. Jody Wages is at our Experience Center. Now, these breakers, this breaker here, this breaker here, this breaker here, this breaker here has a remote operation. Freaking awesome. Absolutely phenomenal. Now, if these breakers are zone selectively interlocked, go Jake, go. So, if those breakers are zone selectively interlocked, you don't know that they're zone selectively interlocked, do you? There's no indication. Until Eaton came out with their new trip units, will give you that indication that they are actively zone selectively interlocked. And we have test protocols, and we have just some sweet stuff. The biggest issue that I would have as either an inspector or a maintainer, if I didn't install those twisted pairs, Jacob, that Jacob called out, if I did not install those twisted pairs in that equipment and see it with my own eyes, I say oja, eyes in Spanish, oja, and I have to do my 10 minutes of Spanish, my Duolingo. If I didn't see it with my own eyes, I would not know that they're zone selectively interlocked. I have no indication, none whatsoever. So you'd have to look at the drawings and then trust that they are actually zone selectively interlocked. What we added, recognizing the fact that that is a critical piece of information. Our new trip units, Eaton's new trip unit. Eaton, woo, woo, woo. Eaton's new trip units have that indication on them. So, and I can't say enough about these devices here to get you out of the arc flash boundary. These blue lights, that's the arc reduction maintenance switch. What about the clear tube around the inside of the trips on light from arc flash? That's the arc quencher, Robert. That's the OHOS. That's the arc quencher. So the arc quenching technology is those light strips, the light sensors, and all that jazz. So in any case, I think one of the best features that we added on our zone selective interlocking was to provide the indication that it is zone selectively interlocked and they are functioning. You can test the zone selective interlocking scenarios through the displays on the breakers, run different scenarios. We also have test equipment that we can put in place to test the functionality of complex zone selectively interlocked systems, because when you're doing main tie mains, wow, it gets crazy. It really gets crazy. You got to know what you're doing. So in any case, zone selectively, we covered a lot of material. We covered the labeling and marking for the electric vehicle charging equipment, some of the code issues, language issues that we've got there, and some of the opportunities for growth in the code, and the wrong references. We covered selective coordination, what it is. We covered what differential, how zone selective interlocking doesn't get you there. Differential relaying doesn't get you there either. So don't use differential relaying thinking you're going to get zone selective, you're going to get selective coordination. Remember, it's about the fault currents, the time current characteristic curves. Don't get lazy on me. Throw that word characteristic in there. And then we talked about 23095, ground fault protection of equipment. Gave you some of my personal opinions there. 24087, 24067. We talked equipment protection. We talked Jody Wages getting out of the arc flash boundary with his jacket, with his cool looking shirt on and all that jazz. Jacob Riddles, he helped us understand that twisted pair. And I'm just going over making sure we covered everything, because I'm realizing now I'm at 2 hours. I should have given CEU credits out. I don't know. Ryan Jackson, helped him understand. We went through the zones of protection. And I do want to say David Engelhardt came in late. He may be late, but he's worth the wait. James Rossman, thanks for joining us. Robert from Omaha, Ryan Jackson, Stephen Froming. All right, and Ryan bought me a free beer. Thank you. And you know beer's going up, Ryan, just saying. All right, so we had some, I enjoyed this session. It is 2 hours, way too much. I got to go upstairs. It's Friday night, and I ain't got no money. And it's 7 o'clock. I told Bobby Joe I would be up at 6. I'm an hour late, so. And she baked a cake. They're having my sister-in-law and my brother-in-law are having a contest. They each make a cake. We're not allowed to know whose cake is which. We taste the cake, which will be tomorrow night, and then we vote on whose has the best cake. Yes, David. Hey, yeah, thank you, Jacob. Thanks for coming in. Thanks for Ryan. And David, go back, take a look at the beginning, because there's some labeling stuff on EV chargers that I found very interesting, and what the labeling requirements are. I'd love to hear your opinion on that, brother. All right, everybody, listen, it's Friday night. Go have a beer and all that jazz. Yes, they do test with flashlights. They test. You need like 3 things to go off at the same time, Robert, from an arc quencher perspective. So it's pretty cool technology. All right, everybody. Remember to stay safe. Remember to stay out of trouble. Thanks for what each of you do for the electrical industry. Some of us do more than others. And I would say each of us does what we can do and contribute to the electrical industry in our own ways, right? So thank you for all that you do. Fish Friday. Take care. Stay safe. God bless. Please stay healthy. See you next week, hopefully.